Here's the big one. How do you teach a model what a good answer even is, when good is this fuzzy human thing nobody can write down as rules? The answer is a reward model, the real engine behind RLHF. Think of a taste tester. A chef plates 2 dishes, the tester takes a bite and says, "This one's better." A reward model is that tester but for answers. Show it a reply, it gives back a score. So what does it do? You hand it the prompt and one response together, and it gives back not more words, just one number. Higher means better. You've squeezed this whole messy idea of quality into one dial you can optimize. And here's a slick part. You don't build it from scratch. You start from your fine-tuned model, which already understands language, and swap its word-predicting head for a tiny one that outputs the score. Now how do you train it? You collect a pile of human comparisons. People see 2 responses and pick the one they like better. Its whole job is to give the preferred answer the higher score. And here's a subtle trap. You don't ask humans to rate an answer 7 out of 10, because my 7 and your 7 mean different things. It's far more reliable to just say this one's better than to pin an exact grade on it. And that's the reward model. You've turned messy human taste into a number a machine can chase, the bridge from what people prefer to what a model can be trained on. And here's what gets you the offer. The ones who get hired say, this score is just a stand-in for human judgment. It's a proxy, not the truth, and the model will game it if you let it. Knowing its limits is the job. So go train a little taste tester on real preference pairs and watch it score. The free notebook is in the bio. Okay, real talk. A human looks at 2 chatbot answers and says, yeah, I like this one better. How do you turn that little shrug into something a model can actually learn from? That's the whole game today. Think about chess rankings. Every player has a hidden skill number. If yours is way higher than mine, you'll probably win. If we're close, it's a coin flip. Bradley Terry says answers work exactly the same way. So we give every answer a score. We call it the reward, and it's just the model's gut feeling for how good the answer is. Higher reward, better answer. Now here's the clever part. We don't care about the raw scores at all, only the gap. Take the reward of the answer the human liked, subtract the reward of the one they passed on. Just the difference. Then you squash that gap through a sigmoid, a little S-shaped curve that bends any number into a probability between 0 and 1. A big positive gap lands near 1, super confident. A gap near 0 gives you a half, a coin flip. And that's it. That's Bradley Terry. The chance a human prefers the winner is just the sigmoid of the reward gap. One shrug turned into a number you can train on. And notice what falls out of this. Because only the gap matters, the scores are totally relative. Add 100 to every answer and the preferences don't budge. The model never learns some absolute good, just who beats who. Here's what gets you the offer. Anyone can write the formula down. The person who gets hired can tell you why we only use the gap, and what it means that the reward has no fixed 0 point. That's reciting it versus getting it. So don't just memorize this one. Go build it from scratch and watch a pile of human comparisons turn into real scores. The free notebook's in the bio. Okay, so you turned human preferences into probabilities. Cool. But a model doesn't learn from a vibe, it learns from a loss. So what's the one number you push down to make this thing actually train? Let's build it. Picture a confidence quiz. You don't just pick an answer, you say how sure you are. Bet big on the right one, tiny penalty. Bet big on the wrong one, ouch, huge penalty. That's the spirit of this whole loss. So we start with what we already have. The sigmoid of the reward gap, the model's probability that the winning answer really is better. When the model and the human agree hard, that number's close to 1. Now take the log of that probability. Logs have this lovely shape. Near 1, the log is basically 0, no complaints. But as the probability slides toward 0, the log dives off a cliff toward negative infinity. Confidently wrong gets punished hard. Here's the gotcha people forget. That log is negative and training always minimizes. So flip the sign, make it positive. Now a confident correct call gives a loss near 0, and confidently wrong gives a giant loss. Exactly what we want to shrink. Then do that for every comparison in your data set and average it. That's the expectation part. One clean score that says, across all these human picks, how badly is my model still disagreeing? And that's the reward model loss. The negative log of the sigmoid of the reward gap, averaged over your data. It's literally the negative log likelihood of the Bradley-Terry model, just dressed for training. And here's the offer getter. They'll poke at it. Why the minus sign? Why a log at all? If you can say the log punishes confident mistakes and the minus is just because we minimize, you're not reciting anymore. You get it. So go code this loss from scratch and watch it drop as the model learns to agree with people. The free notebook's in the bio. Alright, you want to teach a model what a good answer looks like. Simple question, but it trips people up. What exactly do you put in front of it? The answer's way less obvious than you'd think. Your first instinct is the obvious one. Have people rate each answer 1 to 10. But here's the trap. My 7 and your 7 are nothing alike. One grumpy rater, one generous rater, and your scores are pure noise. Absolute scores from humans just don't hold up. So think about a wine tasting instead. Nobody scores a glass 87 out of 100. They pour 2 and ask, which do you prefer? And that people are shockingly good at. Comparing beats grading every time. So that's the data. Comparison data. One prompt, 2 answers to it, and a human just points at the better one. Every example is a little trio. The prompt, the answer they chose, and the one they rejected. And this clicks right into what we built earlier. The model only ever learns from the gap between 2 answers. So we don't need absolute truth, just a steady stream of this one beats that one. Relative calls people can actually agree on. And you need a lot of these. Like a lot. One famous set, Anthropic's helpful and harmless data, has roughly 170,000 comparisons. That's the volume it takes for a sense of good that actually generalizes. And that's the whole input recipe. Piles of prompts, each with a chosen answer and a rejected one. Feed that in, and out comes a model that can rank answers it's never seen. No one ever wrote down a single absolute score. And here's what gets you the offer. When they ask why comparisons instead of ratings, don't just say it works better. Say humans are reliable at relative calls and terrible at absolute ones, and the reward setup only needs the gap anyway. That's the why. So go load real comparison data yourself and see exactly how it's shaped. The free notebook's in the bio. So you trained a reward model, the loss went down, looks great, and then it quietly starts rewarding garbage. This is the question that separates people who have shipped this from people who have only read about it. What goes wrong? Here's the mental model. Your reward model is a slightly lazy judge. Instead of doing the hard work of checking if an answer is correct, it grades on surface stuff that happens to correlate with good, and it picks up some really bad habits. Habit 1, length bias. In the data, the better answers were often a bit longer, so the model takes a shortcut. Longer must mean better. Now it rewards rambling, padded answers just for being long. More words, more reward, regardless of substance. Habit 2, sycophancy. People thumbs up answers that agree with them, so the model learns flattery scores well. Now it'll happily tell you you're right when you're flat out wrong. It learned to please you, not to be honest. Habit 3, formatting bias. Tidy bullet points and bold headers look authoritative, so they win comparisons. The model rewards the costume instead of the substance. It'll take a pretty, well-formatted, wrong answer over an ugly correct one. Habit 4. Distribution shift. Your judge only ever saw certain kinds of prompts. Show it something genuinely new, far from training, and it's basically guessing. Confident-sounding scores on stuff it has no real clue about. And the big scary one, reward hacking. Another model is being trained to maximize this judge's score, so it hunts for every blind spot, every weird quirk, and exploits it. You get answers that score perfectly and are total nonsense to a human. And that's the through line behind all 5. The reward model is just a stand-in for what humans actually want. The moment you optimize hard against a stand-in, every little flaw in it gets ruthlessly exploited. And here's the offer getter. Anyone can list these failures. The hired answer names the root cause. The reward model is a proxy, and hard optimization against any proxy breaks it. Say that, and they know you've wrestled with this. So go train one yourself and try to catch it cheating in the act. The free notebook's in the bio. Okay, you need a reward model, something that reads an answer and spits out a quality score. So do you train a whole new brain from scratch? Absolutely not. And how you dodge that is a classic interview question. Think of it like this. You've got a brilliant novelist who already understands language deeply. To make them a book critic, you don't teach them to read again. You just hand them a new job. Instead of writing the next word, now rate this. Same brain, new output. So you start from a model already fine-tuned to chat, what people call the SFT checkpoint. It already gets grammar, facts, tone, all of it. That hard-won understanding is exactly what we want to reuse, not throw away. Now, a language model normally ends in what we call a head, a layer that looks at the model's thinking and scores every possible next word, the whole vocabulary, tens of thousands of options. Great for writing, useless for grading. So here's the move. Rip that head clean off and bolt on a tiny new one. Instead of a score per word, this layer outputs exactly one number, a single scalar. That's the reward. And this is the part people forget in the interview. You replace the head. And one subtle detail. Which moment of the model's thinking do you score? You take the hidden state at the very last token, the end of the answer. Why there? Because by the final token, the model has already read the entire response. That moment holds the whole picture. And that's the whole conversion. Keep the body, swap the word-predicting head for one that outputs a single number, read it off the last token. Boom! You've got a reward model, barely any surgery at all. And here's the offer getter. They'll ask why start from the fine-tuned model instead of fresh. Say judging quality needs the same language understanding as writing it, so you reuse it. And you read the last token because that's where the full answer has landed. That's the why. So go do the swap yourself. Take a real model, replace the head, and watch a single score come out. The free notebook's in the bio. Here's a moment that humbles everyone training these models. Your reward score is climbing, the graph looks beautiful, and then you read the actual outputs and they're garbage. How does that happen? That's reward hacking, and they love to ask about it. The key thing to hold on to is that the reward model is not the truth. It's a stand-in for human taste. It's an approximation, and any approximation has gaps, places where it's wrong. Imagine you pay a coder per line of code they write. What do you get? Mountains of bloated, padded code. They're not cheating exactly, they're just optimizing the thing you actually measured instead of the thing you wanted. And that's precisely what the model does. It's a relentless optimizer, so it hunts down every crack in the reward model. It finds the inputs that score high for the wrong reasons, and it pours everything into those. High score, genuinely worse answers. In practice, it looks like a few classic moves. Answers get really long because longer often scores higher. It repeats confident-sounding phrases. Sometimes it stumbles onto strange word sequences that just happen to spike the score. So what holds it back? The main defense is the KL penalty we talked about. By forcing the model to stay close to its sensible reference version, you make it expensive to run off chasing those weird exploits. It can improve, but it can't go feral. So the real lesson is bigger than one bug. The reward is a proxy, and the model will exploit any proxy you hand it. That's why you never trust the score by itself. You keep reading the outputs. Anyone can define reward hacking. The person who gets the offer explains why it's almost inevitable. The reward is an imperfect proxy and the optimizer is ruthless, and points to the KL penalty as the main guardrail. That's the answer that lands. So go train one with a weak reward model and watch it learn to cheat in real time. Honestly, seeing it happen is the best way to get it. The free notebook is in the bio. So RLHF has this reputation among people who actually run it. It's twitchy. It can be going great and then just fall off a cliff. And interviewers love to ask, why is it so unstable and what do you do about it? Picture balancing a tall pole on your palm. Tiny wobble, and if you overcorrect it swings the other way and crashes. RLHF is like that. Lots of moving parts and small errors can amplify fast. So let's name where the wobble comes from. First source, the reward model is imperfect. It's a stand-in for human taste with blind spots, and the moment the model finds those blind spots, it chases them. You're optimizing against a slightly wrong judge, and that's destabilizing on its own. Second, the learning signal is noisy. Reinforcement learning updates have high variance, meaning the direction to improve jumps around a lot between batches. It's like getting wildly different advice every day. Hard to steer a straight line through that. Third, that tug-of-war between chasing reward and not drifting too far is genuinely sensitive. Nudge the balance a little and you can tip from learning nicely into reward hacking. The setting that works is a narrow window. So how do you steady it? First, you tune that leash carefully, the KL coefficient. Get it in the right window and you keep the model improving without letting it run off. This is the single biggest lever you've got. Next, you make the reward signal calmer. You can average several reward models together, an ensemble, so no single one's blind spot dominates. And you normalize and clip the scores so a few wild outliers can't jerk training around. And then you just move gently. Low learning rate so each step is small. Clip the gradient so no update explodes. And keep the runs short with frequent checkpoints, so when it does start to wobble, you can roll back to a good spot. So that's the shape of it. RLHF is unstable because the judge is imperfect, the signal is noisy, and the balance is delicate. And you tame it not with one magic fix, but with a stack of small, careful guardrails. Anyone can say lower the learning rate. The person who gets the offer pairs each cause to its cure, imperfect reward to ensembles, noisy gradients to clipping, touchy trade-off to careful KL tuning. That's the answer that lands the offer. So go break it on purpose, push the learning rate too high, drop the penalty and watch it diverge. Then add the guardrails back one by one. That's how it sticks. The free notebook is in the bio. Okay, this one comes up constantly now. Online versus offline RL for tuning these models. People throw the words around, but the actual difference is simple and it really matters. Let's nail it down. Here's the single question that splits them. While you're training, does the model keep writing brand new answers to learn from? If yes, that's online. If no, you're learning from a fixed pile collected ahead of time, that's offline. Everything follows from that. Think of two ways to learn tennis. Online is a live coach watching you swing right now and reacting to this exact shot. Offline is studying a textbook of other people's matches. fresh personal feedback versus a fixed record you read from. Online RLHF is the PPO approach we've been building. Every step the current model writes fresh answers, the reward model scores them, and you update. The data is always about the model as it is right now. Live feedback constantly. Offline is the DPO style. You collect a dataset of preference pairs once. This answer beat that answer, and you just train on it. No writing new answers during training at all. You learn straight from the frozen comparisons. So why bother with online? Because the feedback is always about the model's current mistakes, not someone else's old ones. That makes it more sample efficient. It tends to learn more from each piece of data. The live coach really is more effective per lesson. But here's the catch, and it's the whole trade-off. Online has to generate fresh answers every single step, and we just saw generation is the slow, expensive part. Offline skips all of that. So online is more effective but a lot more costly to run. So that's the real split. Online means fresh answers, better learning per sample, heavy compute. Offline means a fixed dataset, no generation, way cheaper and simpler. It's a genuine trade, not one beating the other. Anyone can say online generates and offline doesn't. The person who gets the offer names the trade-off. Online is more sample efficient because the data is fresh, but far more expensive because generation is the bottleneck. That's the answer that lands the offer. So go build both, an online loop and an offline one, and feel the cost and the data hunger trade against each other. That contrast is where it clicks. The free notebook is in the bio. So here's a question that sounds like a trap and kind of is. During training, your reward score just keeps climbing, higher and higher. Is that good? The honest answer is not necessarily, and knowing why is the whole point today. The key is to hold two things apart. There's the proxy reward, the score from your reward model, and there's the true reward, what real humans actually think. You can only ever measure the proxy. The true one is what you secretly care about. There's an old idea that nails this, Goodhart's law. When a measure becomes a target, it stops being a good measure. The second you optimize hard for the number drifts away from the real thing it was supposed to stand for. It's teaching to the test. Push a class to maximize one exam score and the scores go up, sure. But at some point, they're just drilling test tricks and real understanding actually drops. The metric climbs while the thing you wanted quietly sinks. And that's exactly the shape you see here. Early on, pushing the proxy reward genuinely helps, true quality rises with it. But past a point, true quality peaks and then starts falling, even as the proxy keeps climbing. That gap is overoptimization, and it's the trap. And the reason is familiar. The reward model has flaws, and a relentless optimizer hunts them down. So it keeps winning points by exploiting the judge's blind spots rather than by actually getting better. The score is real, the improvement is fake. And this isn't just folklore, it's measured. Gao and colleagues studied it carefully in 2023 and mapped out exactly that curve, the proxy and the true reward splitting apart as you overoptimize. Nice to be able to point to the actual work. So how do you push back? The KL penalty keeps the model from straying into exploit territory. Ensembles of reward models cover each other's blind spots, and you periodically retrain the reward model on fresh comparisons, so its blind spots stop being so simple to exploit. So the big takeaway is almost philosophical. More optimization is not always better. There's a point where chasing the score harder actively makes your model worse. Knowing where that turn is, that's the real skill. Anyone can say the model overfits the reward. The person who gets the offer draws the proxy versus true reward curve, names Goodhart's law and lists the fixes, KL penalty, ensembles, retraining. That's the answer that lands the offer. So go train past the sweet spot and watch the proxy score climb while the real quality rolls over and drops. Seeing that curve with your own eyes is the lesson. The free notebook is in the bio. So they ask you a sizing question. How big should your reward model be compared to the policy you're training? Sounds like trivia. It's actually about whether your whole training run quietly falls apart. Here's the picture. Your reward model is a referee, and the policy is a player trying to score points. A sharp, experienced referee catches the cheap fouls. A tired rookie ref misses them, and the player learns to milk every blind spot. The score the referee hands out is the proxy reward. What you actually want is the true reward, the gold standard, what a careful human would say. And those two things are not the same. The proxy is only ever a guess at the gold. And here's the danger. Push the policy hard enough and it stops getting genuinely better. It just learns to please the referee. The proxy score keeps climbing while the real quality stalls or drops. That's overoptimization, and it's the thing that bites you. So what does a bigger referee buy you? Gao and the overoptimization scaling paper measured it. As the reward model gets larger and sees more preference data, the gap between the proxy score and the real gold shrinks. Fewer blind spots to exploit. And that's the payoff. A bigger reward model can take more pressure before it breaks. You get to push the policy further, optimize harder before it starts gaming you. More headroom, plain and simple. And that gives you the rule of thumb people actually use. Your reward model should be at least as big as the policy it's judging. You don't want the player smarter than the referee. That rarely ends well. Here's what gets you the offer. Anyone can say bigger is better. The hired answer names why. The reward model is a proxy. A bigger one shrinks the gap to the real goal so you can optimize longer before overoptimization kicks in. That's the part they're listening for. So go train a couple of reward models at different sizes and watch the gap to the real reward close up. That's when this clicks. The free notebook's in the bio.